Hi, and welcome back to the course on Physics for Engineers. This is now the last lesson for Chapter 10. So let us first review some concepts. So in the previous lesson, we have discussed about the first law of thermodynamics. So it pertains to the change in internal energy of the system, which is just the heat absorbed or released by the system minus the work done or by the system. So we also have discussed about the four thermodynamic processes. We have the adiabatic process, no heat flow, no heat flow into or out of the system, isochoric process, constant volume process, isothermal constant temperature process, and isobaric constant pressure process. So in this last lesson, we will now be wrapping up this chapter with the second law of thermodynamics. So the second law of thermodynamics is actually concerned with the natural thermodynamic flow. So natural thermodynamic processes are actually irreversible processes. So heat flows from high temperature to low temperature, and it irreversible processes proceed spontaneously in one direction, such as converting mechanical energy into heat. So in this example, this is an example of a natural heat flow. So heat flows from the higher temperature corn to the low temperature butter. And this process is irreversible. You cannot take the butter back, which is already melted onto the corn. So another example of a reversible process when you rub your hand. So by rubbing your hand, that's actually you are actually converting mechanical energy into heat. So you will notice that your hands will increase in temperature. So reversible processes are actually processes that proceed in one direction and the other. So again, reversible processes are not natural processes because natural thermodynamic processes are irreversible. So example of this is an isolated system. You have a metal box and ice inside, but this is isolated from the system. So therefore, the ice inside can go back from being solid to liquid and being solid again. So it's a quasi reversible process. By the way, sorry, the first one is an irreversible process. The box is actually not isolated, thermally isolated from the surroundings, but in this case, the box is at the same temperature as the ice. So in this case, it can phase change from solid ice to liquid water. So reversible processes are quasi-equilibrium processes, such as this one in letter B. Second law of thermodynamics is also concerned with entropy. So entropy is defined as the disorder of a system or the increase in randomness. So it is involved in converting heat to mechanical energy. So there are actually three statements for the second law of thermodynamics. There is the engine statement, which states that it is impossible for any heat engine to convert heat completely into mechanical work. The refrigerator statement states that it is impossible to transfer heat from a cooler region to a hotter region without doing work because heat naturally flows from hot to cold. So you cannot let flow heat from cold to hot without doing some intervention, without doing work. And the last statement is it is impossible for any system to have a decreasing entropy or to have a decreasing disorder. So in any thermodynamic system, it's always increasing entropy. Okay. So let's first start with the engine statement. So a heat engine is any device that transforms heat partially or partly into mechanical energy. So an automobile engine, the human body is an example of a heat engine. So this is the flow diagram for a heat engine. So the heat engine is located in this circle here. It absorbs heat from a hotter region and uses that heat to do work and releases some of that heat into the colder region. So uh, if you think of the human body, for instance, you absorb food, you do work, and then you poop or you pee. So that is the flow of heat in the human body. So heat engine, the simplest heat engine undergoes cyclic processes, meaning the change in internal energy is zero. That means that the total work done is equal to the total heat absorbed or released by the system. So the total heat absorbed by the system is just the heat input QH and the heat output QC. So in this case, for a heat engine, Q sub H is the heat absorbed from the hotter region, and it's actually positive because it's absorbed by the engine. QC is actually released, so meaning QC is negative. So QH here is positive, QC is negative. And the work done, so since change in internal energy is zero, so the work done is just equal to the total heat, net heat, which is just heat absorbed plus heat released to the colder region. So this is the work output. So to determine the thermal efficiency of the engine, or the measure of how good an engine is in converting heat to work, you just take into account, take the ratio of the output over the input. So the output is the work, the input is QH, the heat input. So take the ratio of that and you will get the efficiency. So you can also do 1 plus QC plus QH. So again, from the engine statement of the second law of thermodynamics, it is impossible to convert heat completely into work. There will always be heat released by the engine. So meaning, it's impossible for an engine or a heat engine to have a 100% efficiency. That is not possible. So there's no human being that doesn't poop. There's no human being that doesn't pee. So all of the food that you eat will be partly converted into work, and most of that actually will be excreted or released to by your body. So a gasoline engine actually undergoes an Otto cycle. This is an Otto cycle. So it starts out with an adiabatic expansion, and then it releases heat. It starts with a compression, an adiabatic compression, and then it absorbs heat and undergoes isochoric process, and then again it undergoes an adiabatic expansion, so no heat involved in adiabatic processes, and then it releases heat in an isochoric process. So that is the thermodynamic cycle for a gasoline engine. It's called the Otto cycle. So gasoline engines have 0.56 or 56% thermal efficiency, theoretical efficiency, but real gasoline engines actually do only have 35% efficiency, which means only 35% of the gasoline fuel taken in by your car or your motorcycle is used in doing work. The remaining 65% is released as exhaust. So that is how inefficient is a gasoline engine. If you have a diesel engine, this is the cycle of the engine. This is what we call the diesel cycle. So in the first part, in the second process, after the adiabatic compression, instead of an isochoric process, it undergoes an isobaric process. So that is the difference between the gasoline cycle and the diesel cycle. And it actually improves the theoretical efficiency of diesel engine from 65 to 70%. So diesel engines are much more efficient as compared to gasoline engines. So let's now go to the second statement, the refrigerator statement. So a refrigerator is just a heat engine operating in reverse. So according to the second law of thermodynamics, the refrigerator statement, it is impossible for heat to flow from a cooler region to a hotter region without doing work, because the natural flow of heat is from a hotter region to a colder region. So, but you can let it flow in the reverse if you do work on the refrigerator. So right now, in the refrigerator, you're actually doing work. So refrigerator usually have pumps. So they have heat pumps. They pump heat from the inside of the refrigerator. They pump heat to the outside of the refrigerator. So still the same, the work done on the refrigerator is just a total heat. But in this case, QH is now negative because this is now heat released by the refrigerator. And QC is positive because this is the heat absorbed by the refrigerator. So the refrigerator actually absorbs heat from anything that you put inside it. So if you put food or water inside your refrigerator, it actually absorbs that heat and then releases that heat outside or at the back of the refrigerator. So that's how a refrigerator basically works. So this work is now work input. In the engine, it's work output. So the efficiency of a refrigerator is given by the coefficient of performance. So it's proportional to the EER, energy efficiency rating. So when you buy an air conditioner or when you buy a refrigerator, by the way, an air conditioner and a refrigerator works in the same principle. If you buy an air conditioner or a refrigerator, you actually see some yellow tags and there's an EER rating there. So that's an energy efficiency rating. It is proportional to the coefficient of performance of your refrigerator. So the coefficient of performance K is actually the absolute value of QC, the heat absorbed from the cold region from inside the refrigerator over the work input of the refrigerator. That one. Or it can also be equal to QC over QH minus QC. So take note of the absolute value signs. Okay, there's a special cycle called the Carnot cycle. So in the Carnot cycle, you can have a Carnot engine or a Carnot refrigerator. So a Carnot engine is a hypothetical idealized heat engine that has the maximum possible efficiency. This was developed by C.D. Carnot. So this is the Carnot cycle. It has 4 steps. The first step is an isothermal expansion, and then adiabatic expansion, and then you have isothermal compression and adiabatic isothermal compression and adiabatic compression. So the efficiency of a Carnot engine, so it's just take a Carnot engine is a theoretical engine. It's the which has the maximum possible efficiency, and its efficiency is work input over heat work output over heat input, and or it's 1 minus the temperature of the cold region over the temperature of the hot region. So it only depends on the temperature of your hot and cold regions. It doesn't actually depend on how much heat or how much work you do. So only on the temperatures of the cold and hot regions. So if you have a Carnot refrigerator, it's just a Carnot engine operating in reverse. So the reverse of this process. So instead of expansion first, you have compression. And the coefficient of performance also depends on the temperature of the cold region and the temperature of the hot region. So it's TC over TH minus TC. But again, for both the efficiency and the coefficient performance of the engine and the Carnot engine and Carnot refrigerator, you can still use the original formulas for efficiency and coefficient of performance. Okay. We will not be doing some calculations with the entropy, so I will just restate the entropy statement again. It is impossible for any system to have a decreasing entropy or disorder. Natural processes always tend to disorder, meaning our society, for instance, is actually going to disorder. if you don't just leave things as they are. But if you do some interventions, of course, you can maintain order. So example of this is the firecracker. The firecracker explodes. This order increases. The neatly packed chemicals within each firecracker disperse in all directions, and the stored chemical energy is converted into random kinetic energy of all the fragments. So this is an example of an increasing disorder. You cannot put this back into order, but there are things that you can put back into order. This is also another example of an increasing entropy. So when you mix ink with water, it will actually disperse equally in the water and increasing the entropy of the water or the system, our system. So you cannot take this back. You cannot decrease, you cannot make the water clear again, maybe unless you do some chemical interventions. So that. Okay, let's now have an example of the topics on the second law of thermodynamics. Okay, this is now a follow-up of the example in the first law of thermodynamics. So you have the same problem. You propose to eat 180 food calories, so that's 180,000 calories of hot fudge sundae with whipped cream, and then run up several flights of stairs to work. So how high do you have to climb? Assume that your mass is 60 kilogram and that the efficiency of your human body is 25%. So you assume your body is a heat engine with an efficiency of 25%. Okay. So the efficiency of a heat engine is just equal to the work output over the heat input. So our heat input here is this one, 180,000 food calorie. And our work is the work done by gravity, essentially, mgy over qh. So solve for y again. So y is just equal to cross multiply, you have E QH over mg. So in the previous problem, we didn't take into account the efficiency. So we only have this one, Q over mg. But it's now multiplied by the efficiency, in this case 25%, which means we will have 25% of our previous answer. So our previous answer here is actually 1,280 something. So 25% of that is 320 meters. So in the previous problem, you actually have to climb 300 stories of stairs, 300 story building. But in an actual problem, taking into account the efficiency of the human body, you only need to climb 20%, 25% of that. 25% of 300 is 75. So you only have to climb not a 300-story building, but only a 75-story building. So 320 meters in order to burn all of the 180,000 heat calories that you have absorbed or eaten. Okay. Example 2, analyzing a heat engine. So we have this heat engine. So a gasoline engine in a large truck takes in 10,000 joules of heat and delivers 2,000 joules of mechanical work per cycle. So take note, this is a cyclic process. So for every cycle, it takes in 10,000 joules of work. It do 2,000 joules or 10,000 joules of absorbs 10,000 joules of heat. Then the engine does 2,000 joules of work, and then repeat again. Another cycle, it absorbs again 10,000 joules of heat and then do 2,000 joules of work. So the heat is obtained by burning gasoline with heat of combustion of this one, LC. So LC is latent heat of combustion, 5 times 10 to the 7 joules per kilogram. So what is the thermal efficiency of this engine? So first question, what is the thermal efficiency of this engine? Okay. So efficiency is just work output over heat input. So in this case, you have 2,000 joules output and then 10,000 joules of heat input. So you will get 0.2 or 20%. So the efficiency of this engine is only 20%. So actually this is very true for very large automobiles, very large trucks in this case. 20%, only 20% of the gasoline essentially is used to do work. The remaining 80% is discarded as heat. Okay. For letter B, we are asked to find how much heat is discarded per cycle. So we are looking for QC. So work is just QH plus QC. Therefore, QC is just equal to work minus QH. So work is 2,000, QH is 10,000, so you will get negative 8,000 joules or 8 kilojoules. So it's obvious, right? It absorbs 10,000 joules. It does 2,000 joules of work, meaning it will release 8,000 joules of work per cycle. So this is per cycle. Letter C. If the engine goes 25 cycles per second, what is its power output in watts and horsepower? So power. So power is just work per unit time. So 25 cycles per second, we have 25 cycles per second. So you have, in one cycle, you actually do 2,000 joules of, you actually do 2,000 joules of work, 2,000 joules of work per cycle. So meaning, and you have 25 cycles. So that's the total work in 25 cycles and in 1 second. This is in 1 second. So because you have 25 cycles per second. So in a time of 1 second, there are actually 25 cycles in 1 second. So meaning, if you do 2,000 joules of work per cycle, you multiply that by 25, so that the cycle unit will cancel out. So 2,000 joules times 25, that is actually the work done in 25 cycles and in 1 second. You will get a power of 50,000 watts. The unit called joules per second is watts. And this is equivalent to divided by 746, and you will get 67 HP. So 746 watts is equivalent to 1 horsepower or 1 HP. So that is for letter C. Okay, for letter D, how much gasoline is burned in each cycle? How much gasoline is burned in each cycle? So this is actually a problem on calorimetry. So the amount of heat this is actually QH, the amount of heat burned, which is the amount of heat absorbed by the engine, is actually equal to the mass times the latent heat of combustion. So M times LC. So you have the mass. Are we given with the? Oh no, we are trying to find the mass. How much gasoline is burned in each cycle? So we're looking for how much gasoline, so mass. So the mass is just equal to QH over LC. So QH is 10,000, LC is given by that one, and you will get 0.20 grams. I just converted directly into grams. So your answer, depending on the unit that is required of you, you can answer in kilogram or in grams. So I'm just gonna answer in grams. So every cycle you burn 0.20 grams of gasoline. So for the last question, how much gasoline is burned per second and per hour? So in this problem, for letter E, we are actually trying to find the rate of mass of gasoline burned per hour and per second. So change in M over change in T. So you will get 0.20 grams per cycle, and you have 25 cycles per second. So the cycle unit will cancel out. You will get 5 grams per second. If you convert that to per hour, then this is equivalent to 18 kilograms per hour. Convert grams to kilograms, you convert seconds to hours. So 5 grams per second or 18 kilograms per hour. 18,000 grams per hour. Okay. So as a review, this is the efficiency of the engine, this is the heat released by the engine, this is the power of the engine, 50,000 watts or 50 kilowatts or 67 horsepower, and the mass burned per cycle is 0.20 grams, and the rate of gasoline burned per second per hour is 5 grams per second or 18 kilograms per hour. Okay. Let's now go to analyzing a Carnot engine. So a Carnot engine takes in 2000 joules of heat from a reservoir at 500 Kelvin. So this is the temperature of the hot region. Does some work and discards some heat to a reservoir at 3500 Kelvin. How much work does it do? How much heat is discarded? And what is the efficiency? Okay, so in this problem, we can actually solve for the efficiency first. Since we already know the temperatures, and the temperature of and the efficiency of a Carnot engine only depends on the temperatures of the hot and cold regions. So you have 1 minus Tc over Th. So Tc is 350 Kelvin, Th is 500 Kelvin. If you substitute all of those values, you will get 42.9%, 0.429, 0.43 if you round up in two decimal places and two significant figures. So 42.9%. Okay, so we can now then solve for the heat, for the work done. So the efficiency, since this efficiency is just equivalent to the work done over the heat input, so we can now solve for the work done by our Carnot engine. It's just the efficiency times QH. So the efficiency is that one, 42.9% or 43%, multiplied by QH 2000, and you will get 857 joules. So since work is equal to QH plus QC, then we can now solve for QC. QC is just equal to work minus QH. So we already know the work, we already know QH, and we can now solve for the heat released to the cold region. This is negative 1143 joules. That one. So for this problem, the efficiency is 43%, work done by the engine is 857 joules, and the heat released to the cold region, the heat exhausted by the engine is negative 1143 joules. So for the last example, let us consider a freezer. So a freezer has a coefficient of performance of 2.40, so it's actually a very low coefficient of performance. But so the freezer converts 1.80 kilograms of water at 25 degrees Celsius to 1.80 kilogram of ice at negative 5 degrees Celsius in an hour. So what amount of heat must be removed from water at negative 25 degrees Celsius to convert it to ice at negative 5 degrees Celsius? The first question is actually a problem of calorimetry. So you need to draw your solution here first. So first, you have water, liquid water at negative 25 degrees Celsius. So you have liquid water. at 25 degrees Celsius. And then the final value the final form should be ice at negative 5 degrees Celsius. So before it can become ice, it still needs to go to the freezing point. So it needs to become water at 0 degrees Celsius. And it's now water at 0 degrees Celsius, it can undergo a phase change to become ice at 0 degrees Celsius. So in this scenario, heat is actually released. So there's heat Q1 released, heat Q2 released to become water at 0 degrees Celsius. Then it further releases another heat Q3 to become ice at negative 5 degrees Celsius. So this is a temperature change. This is a phase change. This is a temperature change. So I will leave this as an exercise for you. So Q here, the total heat will be Q1 plus Q2 plus Q3, and you will get a value of negative 8,650 joules. That is for letter A. It's a calorimetry problem. So letter B, how much electrical energy is consumed by the freezer during this hour? So how much electrical energy is consumed by the freezer this hour? So how much energy? So meaning how much work? It's actually how much work. This statement or this question actually converts to how much work is done by the freezer in this hour, in 1 hour. Take note that this energy is just the heat released by the ice or your water. And take note, this is heat released by the ice. And this heat released will be absorbed by the freezer. So this will be absorbed, this heat will be absorbed by the freezer, and then it will further release that at the back of the freezer. Okay, so for letter B, the coefficient of performance is just QC over work. So in this case, QC is just actually negative Q. So this is the heat released, and this heat is absorbed by the freezer. So QC is the heat absorbed by the freezers, and it's negative Q because Q is negative. So it's now positive. So therefore, we can now solve for the work. The work is just equal to QC over K. So you have this one, QC is the positive version of that, divided by K, which is in this case, K is the coefficient of performance, 2.40, and you will get a value of 337 kilojoules. Okay. So that is the answer for this problem. So for letter A, it's negative 809. So I just rounded it up. Kilojoules. And you have 337 kilojoules. Okay. There's still a letter C problem. Sorry. Sorry. Sorry, there's a letter C pala. Sorry. How much wasted heat is delivered to the room in which the freezer sits? So for letter C, we are trying to solve for QH. QH is the heat released to the hot region. So since work is QH plus QC, then QH is just equal to work minus QC. So you already have obtained the work in letter B. And QC is just negative Q, the total heat released by the water. And this will give you a value of negative 1,146 kilojoules. Okay. So these are our final answers. And that's the end of the lesson. And essentially, the end of the chapter on thermodynamics. So in the next chapter, we will be talking about the fourth fundamental quantity, the electric charge. So we'll be all be talking about charges at rest or electrostatics. I will see you again in the next chapter.